everybody, welcome back to Mathematical Statistics. We have been talking about wonderful properties of maximum likelihood estimators. I had a list for you consisting of 5 or 6 things. I'm not going to recap it. I will recap it as we go today. But first, we were in the middle of talking about Jensen's inequality. And in the proof of Jensen's inequality, and I will recap the inequality as well, I did use a fact. So let me get my screen here. Okay, so along the way in the proof of Jensen's inequality, I used something like this. It didn't look exactly like this. What I had was an inequality involving random variables, and I took the expectation right across the inequality. So I'm willing to bet a lot of you didn't even bat an eye at that, but why can we do this? One thing towards explaining this is to even know what this means. If you have 2 random variables and one is less than or equal to the other, if you were to go make observations, go roll those dice or flip those coins and record your zeros and ones and whatever, don't they come out, random and jumping around? And why would one always be less than the other? One example could be that the random variable x has support 1, 2, 3, and the random variable y has support 4, 5, 6. But more generally, this means that you have this inequality with probability 1. So that's just what it means to write the thing in the circle. So if we have the thing in the circle and we define a new random variable z to be y minus x, then we have that z is greater than or equal to 0 with probability 1. So z has a probability mass function or a probability density function, or maybe it doesn't. Sometimes these things don't even exist, but that's a different course. And all the values, the support of this distribution is on non-negative values, whether they're real or integers or some finite set in there. So if all the values for z are non-negative, then when you weight them by their respective probabilities and sum those and divide, so when you compute the probability weighted average or expectation of something that's non-negative, that is definitely non-negative. So this is going to imply that the expected value of z is greater than or equal to 0. We're averaging things and nothing's negative in there, so there's no way, even though we're weighting those values by positive numbers, there's no way that average is going to be negative. So expanding again what z is, this is saying the expected value of y minus x is greater than or equal to 0. And if you run the expectation through and then reorder things, this tells you that the expected value of x is less than or equal to the expected value for y, which is what we wanted, which is what I used in the proof of Jensen's inequality. So in case you were wondering, and again, probably a lot of you are not wondering, that's what you can do when you have an inequality and run expectations through. The biggest part to understanding this is to know what an inequality for random variables even means, because this thing is just an inequality involving real numbers. Expectations are not random, and so we know what this inequality means. And now, if you didn't before, you know what this inequality means. Let's return to Jensen's inequality. This is something that's usually stated for convex functions. So if g is convex, and if you want to use your calculus terminology, this would be concave up, meaning it opens upward. So something like this, then we have a result. Now, the definition of convexity is not to do this with your hands. The definition of convexity is that if you look at any point on this curve and look at the tangent line is completely below or equal to the function g. And that's, in fact, the basis for our proof of Jensen's inequality last time. So I don't want to drag you through that again, but our result was that g of the expected value of x was less than or equal to the expected value of g of x. That's Jensen's inequality right there. And so it tells you something about taking expectations inside and outside of a function. If you have a linear function, that's not going to change anything, and you'd have equality here. But if you don't have a linear function, then you can try to narrow it down further. Okay, it's not linear, but it's convex, then you have this result. And if it's concave, and that means from, I can't spell is what it means. If it's concave, and if you're coming from more of a calculus background than advanced analysis and stuff, this means concave down. And this means that the picture has curvature like this if you graphed G. So there is, of course, a version of Jensen's inequality here. And we get it almost directly from what we already did. We don't need to prove this from scratch. If G is concave, if it looks like this curve, this implies that the negative of G is convex. The negative of G is going to be this function, hard to see because of my circle there. And so we can apply the Jensen's inequality we already know and have loved for a limited time to the negative of G. So this means by Jensen's inequality that negative G of the expected value of X is less than or equal to the expected value of the negative of G of X. You can pull this negative out. There's a negative on both sides. If you don't just want to cancel those, you think of it as multiplying both sides by -1. That will flip the inequality. So we'll get G of the expected value of X is greater than or equal to the expected value of G of X. So here's the original Jensen's inequality. This is another version. This one is for convex or concave up functions, and this is for concave or concave down functions. For example, by far the most use we're going to get out of this inequality, what a bad sentence, is on the function, the log in any base, but usually the natural log of x. So this is something that looks like this. It approaches the y-axis asymptotically as x goes down to 0. It crosses the x-axis at 1. And you can see that this is concave or concave down. And so it's this inequality that I've circled in green here that's going to apply. This means that in particular, for this log of x function, the log of the expected value of x is greater than or equal to the expected value of the log of x. I'm going to need this today in our proofs of the nice properties of MLEs. And that's why I brought up Jensen's inequality in the first place. So if you're ready, let's go. I can't remember if I had 5 or 6 things. What did we have? We had existence and uniqueness of the MLE. We had consistency. We had asymptotic unbiasedness, asymptotic efficiency, and asymptotic normality. So we had 5 things, not that there aren't others, but here were our nice properties of MLEs. I want to set the stage first and say that everything I want to prove today, these properties can also hold in the non-IID case, but I am going to restrict my proofs to the IID case. So suppose that x1 through xn are IID from some distribution with PDF f of x and theta. I'm going to change this notation up just for this section of the course as we go through these 5 things and the 5 proofs. Actually, 4 proofs. One of them we're not going to prove. The change of notation is that I am going to change theta out for a theta naught. Why am I doing this? We are going to be working with likelihoods and log likelihoods, and these are functions of theta, and they're maximized at MLEs, and theta is moving around. But there is one parameter that was there under or behind the scenes for generating the data that we're trying to estimate. So because there's thetas running all over the place, I wanted to emphasize that there's one true fixed parameter that generated our data x1 through xn. So I'm going to call it theta naught. And I will just do that for maybe today and Thursday's class. Okay, so I'm going to let theta n hat be n, or a, I guess I'm using an acronym, so n, a maximum likelihood estimator for theta naught. We've used this notation before. I don't always have an n there, but I do want to stress the dependence on n because our MLEs almost always have some dependence on n, like x bar, which is 1 over n, the sum from 1 to n, or xn in parentheses, the maximum of n things, or a sample variance, which is also dependent on the number of data pieces. So I think I've done this before using this subscript here. I don't always use it, but I really want to stress the dependence on n. And is that enough for me to start stating things? Hopefully, I think I'm going to have to go back. Oh yeah, one more thing is under certain regularity conditions. We saw some quote unquote regularity conditions when talking about the Cromie-Rao lower bound. Are these the same? Depends on which property we're looking at in our list of 5 things. But under some niceness conditions, we have the following properties. Rather than compile a list of those conditions, just like I did when we were proving the Cromie-Rao lower bound, we're going to figure out what we need to get the different properties to hold. And whether or not you want to collect them into one big basket of regularity conditions or not is up to you. So if you collect them all together, you can say under this group of conditions, I have these 5 properties. Or you can be a little more flexible and say, I have property 2 under these conditions, but property 3 under these conditions, something like that. So we'll see what we need as we go. Number 1 in our list was that the MLE exists and is unique. And this is going to be wholly unsatisfying. I did say I was only going to prove 4 out of 5 things. I'm not going to prove or give conditions for this because of a couple of things. There's many sets of sufficient conditions I can give you, and none of them really have anything to do with probability or statistics. The question is, when does any function have a maximum existing? And when does any function have a unique maximum? There's so many things I can say here. One example of some sufficient conditions is to say that your likelihood is continuous and the 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 arguments it takes, which is the theta axis, which is the parameters for us. The parameter space is compact. If you don't know what that means, for real numbers, it just means closed and bounded. One way to guarantee that a function has a maximum, and this isn't talking about uniqueness at all, is that it's continuous and you're on some closed and bounded, it doesn't have to be a nice interval, but really nice closed and bounded space, then you are guaranteed to have a maximum there. So this is one set of sufficient conditions, and it doesn't even hold all that much. It's maybe the most popular set of sufficient conditions for a function to have a maximum. But in what we're doing in statistics, our parameter spaces are not often compact. For many things we've needed for our parameter spaces or our PDFs, I've said, yes, this might not happen for something weird, but for all the things in our table, we're fine. But that's not the case here. For example, for the exponential distribution, with rate lambda, the parameter space is 0 to infinity, which is not a compact space. And that doesn't mean that the maximum likelihood estimator for the exponential doesn't exist, but these conditions are not going to do it. Whereas if we look at a geometric distribution, we had this notation, whether it starts from 0 or starts from 1, it doesn't matter. With the parameter p, we had a nice compact parameter space there. So again, one set of sufficient conditions, but my advice to you is you have some data and you're trying to find an MLE, so you have a likelihood. And does it have a maximum? Start taking derivatives. Can you find critical values? Check with second derivatives. Are they maximums or minimums, or did you not find any maximums or minimums? Sketch it if you need to. You're dealing with a concrete function, and you can determine whether or not it has a maximum. And uniqueness is a whole bunch of different questions, but you'll see that too when finding an MLE. If you go to find critical values by taking derivatives and setting them equal to 0, if you get multiple solutions, then you might still have a unique maximum. You might have something that is bimodal. This might be your likelihood. This picture, assuming nothing strange is going on out in the tails, seems to have a unique maximum. But again, it comes down to your specific likelihood, your specific PDFs, the specific functions you're working with. So that's all I'm going to say about property 1 for MLEs. Under conditions, the MLE exists and is unique. Non-uniqueness would be something maybe bimodal, but exactly the same height. Those are the picture awful. Then these would both be MLEs, and that's okay. Okay, so let's go on to something we will prove. And that is property 2 in our list. And I believe these are out of order. I'm sorry, but I believe that we said that theta n hat is a consistent estimator of that unknown parameter, theta naught, that generated the data. i.e., this is a convergence in probability statement. So this is what we want to show under certain conditions. The condition we're going to end up needing here is the variance of something to be finite. We'll see when we get there. So yeah, let's set up some notation. A, not the, a likelihood. I'm going to call this L of theta, as we always do, a capital L. But you know that it does depend on n under there, right? We think of the x's in the likelihoods, like our likelihoods look like, something like this. We think of them as functions of theta, but if the data changes, it does change the likelihood. So, and it does depend on the sample size. So if you have a small sample or a large sample, your likelihood is going to change shape. So I'm going to add to this notation capital L sub n. And I'm going to do one more thing differently here. So a likelihood, if they're IID, is the product, it's the joint PDF, which comes from the product of the f of xi and theta. This is not theta naught. This is, I don't know what theta naught is, so I'm writing down this likelihood as a function of theta, and we're going to try to estimate theta naught by finding an MLE. Because the theta for a likelihood is running over the whole parameter space, so it's not the particular one that generates the data. And so I left a space here, over here. I'm going to do something a little different than anything we've ever done. There's usually a lowercase x sub I in there, and so the likelihood might look something like this. I want to plug random variables in for the x's, so I'm going to put capital X sub I so that I could talk about this function, maybe doing certain things, having certain expectations, or converging in probability to something, and have some randomness in there to work with. So we haven't seen a likelihood before as a function of, or written as a function of random variables, but we could have. You know how we always work our algebra and our calculus, and we figure out what maximizes something, and in the end, we make everything capital. We could have started with everything capital at the beginning before starting off to find an MLE. So this is a little different. Okay, so given this likelihood, so I haven't dropped any constants or multiplied by any constants, the log likelihood is, so I've been calling this this sort of curly script L of theta, And now I'm going to put an n subscript there, and I'm going to try to be careful about how I write that because that's going to come awfully close to looking like my natural log. But this is the log of the likelihood. And if you take the log of this product, you get a sum of logs, capital Xi and theta. So check this out. I am going to put a 1 over n in front of this, which means I get 1 over n, the sum as I goes from 1 to n of the log of f of capital Xi and theta. And this is just an average. It's an average of some y terms. If you call this whole thing yi, then this whole thing is y bar. And we know that a sample mean converges in probability to the true distribution mean for any one of them by the weak law of large numbers if the variance for the y's is finite. So this converges in probability to the mean for any one of them, like the expected value of y1. I'm going to write that out over here as the expected value of the log of f of x1 and theta. If the variance for any one of the y's is finite. So I don't really want to introduce the y notation here. I just did for a moment so that it looks like, an x bar, a y bar in this case. So we do need the variance for the log of f of x1 and theta to be finite. That's how we get the weak law of large numbers to work. So this is by the weak law of large numbers. This variance is the expected value of the thing inside squared minus the expected value of the thing inside all squared. So this finite variance requirement for a sufficient condition to get this consistency result would be the same as saying a finite second moment is required, which also gives you automatically a finite first moment. So we need this, but with like a square. Stop erasing everything. We need a squared in here. We need this to be finite. This is one of our regularity conditions that we're going to need to get this consistency proof to work. And I erased my arrow. Okay, what does this expectation look like? I want to write down this expectation. And it looks like I erased a lot of stuff. I'm sorry about that. F x1 theta. Okay, I want to write down this expectation of the log of f of x1 and theta. Now, this is going to depend, we're going to get a sum or an integral depending on whether the distribution is discrete or continuous. I'm just going to use continuous notation. We could do the analog in the discrete case. And shameless plug for my other course. If you take a course in measure theoretic probability, you learn how to treat the continuous case and the discrete case as one unified case, so you don't have to worry about this sort of thing. But I'm going to choose one, the continuous case. So the expected value of the log of f of x1 and theta is the integral from minus infinity to infinity of the log of f of a little x. Now it's just an argument, so I don't need to call it x1. And theta multiplied by the PDF for capital X1. And our PDF was f of x and theta naught. That's what generated x1 and x2 and x3 dx. So I don't need this explicit expression for the expectation in the rest of the proof, but I just wanted to make sure you knew what this meant and also to see the role of the theta versus the theta naught. This is going to be a function of theta, and this is going to end up being a function of theta, but it's going to be computed using that constant value over here, the theta naught. Theta naught, theta naught. Okay, I have a claim for you. We're almost done here. I claim that this expectation, log f x1 and theta, Now, this is a function of theta, right? There's going to be no x in there because the expectation is there. That's going to be averaged out. It's going to be no randomness. This is a function of theta. I claim that this is maximized at theta equals theta naught. Let's check it out. Consider, so this is my little proof of this claim, the expected value of the log of f of x1 and theta minus the expected value of the log of f of x1 and theta naught. If I can show that this quantity is negative for all theta, then that would mean that this is bigger than this no matter what theta is, and therefore that this, as a function of theta, is maximized at theta naught. Let's pull this together under one expectation, and while we're at it, so I don't have to write a whole new line, we'll have an expectation of a log minus a log, which we can write as a log of a quotient. So this is the expected value of the log of f of x1 and theta over f of x1 and theta naught. This is a function of a lot of things, I guess, but the randomness is x1. So if you want to compute this, you're going to integrate, or sum, minus infinity to infinity of f of little x and theta over, sorry. Actually, I can't do that yet. I can, but it's not going to help. I want to get that log out first. And here's where I want to use Jensen's inequality. Let me remind you up here, way up here, that if the log is outside of the expectation, you get something larger than when the log is inside of the expectation. So right now, my log is inside. So this is going to be less than or equal to, this is Jensen's inequality right here, the log of the expected value of f of x1 and theta over f of x1 and theta naught. So to compute this expectation, this is the integral minus infinity to infinity of f of some little x, it's just an argument, theta over f some little x and theta naught times the PDF for x1. And the x1 through xn were generated using using theta naught. So that's how we write that expectation down. But I get cancellation. And what's left is the integral of a PDF. Right, the parameter, I don't know exactly where it is, but for any fixed parameter theta, we've got the integral over the whole space of the PDF. And the integral is going to integrate to 1. So this is, let me give this its own line. So this is 1. So we've got the log of 1, which is 0. And so we have this quantity is less than or equal to 0. And that means that this quantity is less than or equal to this quantity, no matter what theta is. So my claim is that this is maximized when theta is theta naught. And we've just proven that. Okay, I feel like I'm sure you're feeling it too. Like, what are you talking about at this point? I want to go back to our convergence and probability result that we had with the weak law of large numbers. So we have that 1 over n, the log likelihood, although that's a curly L sub n, that's not my natural log, of theta is converging in probability to the expected value of the log of f of capital X1 and theta. That's something we've already established above. So note that this is maximized at the MLE, which we call theta sub n hat. And this, as a function of theta, is maximized at the fixed parameter theta naught. That's what we just showed. So here I'm going to do a little bit of hand wavy. There's a lot of analysis here. You could use something called an argmax continuity theorem if you want to look that up, but it's really beyond the scope. So let me try to draw what's going on here. Maybe this is where to put things is going to get to be a crowded picture. So maybe this is 1 over 1, the first log likelihood of theta as a function of theta. And then maybe if we move up to a sample of size 2, we get something like this. So maybe this is 1 over 2, the log likelihood, depending on 2 x's as a function of theta. And I can draw one with n equals 3. And this is, in some sense, approaching this function of theta. So maybe this one is over here. So maybe this is the expected value of the log of f of x1 and theta drawn as a function of theta. So I want to get at least one more in here. The first likelihood, the second, this function, and then this function, and then maybe the next one, they are moving towards this pink function. That's what the line at the top of the screen is saying. Now, what is the maximum of my first curve drawn in white here? It happens here, and it's defined to be at theta 1 hat. That's the MLE if we have a sample of size 1. And the maximum on the green curve is here, and this is going to be the MLE from a sample of size 2. Kind of have a yellow curve in here, and this is going to be the MLE from a sample of size 3. And finally, this pink curve is maximized at theta naught. So I claim that if you have this sequence of functions approaching the hard to see pink-purple function, that the maximizers are approaching the maximizer of the pink-purple function. Some of you know that as an argmax, the argument that maximizes these functions. Again, I am going from this result to say that this implies that the maximizers are approaching the maximizer of the final limiting function in probability. Again, there is an argmax continuity theorem, which is what I would start looking for if you were trying to Google results, and it does not depend on probability or statistics, but just analysis and functions and their maximizers. And you're not always guaranteed for this to happen. If you draw really strange pathological functions, you might not get this result that the maximums converge to the maximum, but you will for most likelihoods. Waving hands. This is what we wanted to show. So if you accept that hand wavy part, we are done with the proof of property 2 for MLEs. We have shown that our sequence of MLEs converge in probability to the true parameter that generated the data, capital X1 through capital Xn. All right. The third thing on our list of nice properties of MLEs, and after this one, we'll take a break. And it's an awful lot of theory today. I have to admit, I'm loving it, but I'll do another MLE computational example after this before going on to the other properties so that we can have a little break. This was that the MLE, theta n hat, is an asymptotically unbiased estimator for that theta naught, that special parameter that generated the data. i.e., so what this means is the limit as n goes to infinity of the expected value of the MLE is going to be the right thing. We've already seen more than one example of maximum likelihood estimators that were biased estimators. Sometimes they're unbiased right out of the gate for finite n, but I'm claiming that they'll all be asymptotically unbiased under some conditions. One of them is going to be, well, we're going to see. I promised we would just sort of uncover them. but that the variance of the MLE is bounded. So let's see why we need that. The proof. I'm just gonna admit that right up front. We need the variance of the MLE who be bounded to be less than or equal to some constant C. I'm actually going to save C for something else. But if the variance is bounded, this implies that the second moment of the MLE is bounded, and this implies that the first moment is also bounded. So this is the condition I'm going to impose. It is a sufficient condition to get us the asymptotically unbiased result that we want. And so assuming that, let's see how we get this result. You'll recall that the mean squared error for theta n hat was the variance for theta n hat plus the bias of theta n hat all squared. We just said that we're assuming that this is bounded, and this bias inside the square is the expected value of theta n hat minus the true value, theta naught. And given our sequence of statements up here, this, and therefore this whole thing, is bounded. This would be totally weird and whack, and you wouldn't have data generated from an infinite parameter, so don't worry about that. So if the variance is bounded, that gives us that the bias is bounded, and then looking at this relationship here, this gives us that the MSE is bounded as well. So let's give this a name. Suppose that the mean squared error for theta n hat is less than or equal to some constant C. I don't know. In analysis, you usually use capital letters for bounds, but in prop stat, this looks like random if I make a capital letter. I don't know, make it capital if it makes you feel better. Okay, I'm trying to show that this sequence is converging to this. So let's start off by looking at the distance between those things. I'm going to write down the absolute value of the expected value of theta n hat minus theta naught. This is equal to the absolute value of the expected value of theta n hat minus theta naught. I just pulled the theta naught into the expectation. It's a constant. So looking at the thing inside the absolute value, you can run the expectation through, and then the second term is like the expected value of 3 is 3. The expected value of theta naught gives you just the theta naught back. So that's why we're allowed to put the expectation on both of them. And now I want to use Jensen's inequality on the function g of x equals the absolute value of x. That function, is V-shaped. It is as convex as you can get. And so by Jensen's inequality, I know this is less than or equal to, this is Jensen. Here I've got g of an expectation, and that is less than or equal to the expectation of g of what's inside. So this is going to be less than or equal to the expected value of the absolute value of theta n hat minus theta naught. In fact, we don't even need Jensen's inequality to figure out that this inequality is true, because over here you're averaging things, and then you're taking the absolute value at the end. So that average could be some positive terms and negative terms. But if the absolute value is inside, now you're averaging everything strictly positive. If everything was strictly positive to begin with, the two sides of this inequality are actually equal. But I think this inequality is highly believable, even if you hadn't heard of Jensen's inequality. Okay, so we want to show some convergence, right? I'm going to need an epsilon. I'm going to let epsilon be greater than 0, or take any epsilon greater than 0. And I want to look at this. So yeah, let me rewrite this. I've got the expected value, I've got the absolute value of the expected value of theta n hat minus theta naught less than or equal to the expected value of the absolute value of theta n hat minus theta naught. And now I'm going to rewrite this, the absolute value inside. I'm going to write this with some indicators. I'm going to break it up into that absolute value being either greater than or equal to epsilon or less than epsilon. So this is the absolute value of theta n hat minus theta naught times the indicator that says that theta n hat minus theta naught is less than or equal to epsilon. Doesn't really matter where I put this inequality. Plus, this is all in one expectation, the absolute value of theta n hat minus theta naught times the indicator that says that this distance is greater than epsilon. I think we've used indicators like this. If not, just this is an aside, a marginal note. I don't have a margin here. But you know that an indicator like this is 1 if the argument x is in that interval and 0 otherwise. But if I am just writing like an event like this is going to be 1 if the event happens and 0 otherwise. So this is a little bit different than the other indicator notation that I've been using with parentheses. And hopefully that makes sense. And also hopefully you can see why this long line I've written is the same as this. I just sort of broken it up and I'm looking at it over different regions and yeah. So let's go forward. Rid of these circles and maybe this indicator as well. It's making it a little more messy than it has to be. Okay, the first term in the expectation, I'm going to bound it above. Actually, before doing that, you would run the expectation across this sum. And now I'm going to bound that first term above. So this part is always 0 or 1. The most it can be is 1. And if it's 1, then the most this can be is epsilon. Because when the indicator is 1, that's saying that that quantity is less than or equal to epsilon. So my first term is less than or equal to epsilon. And the second term, I'm just going to leave in place for the moment. And what's going on with that second term? This is a weird step. Unmotivated, you might even say. But I want to set this up for using the Cauchy-Schwarz inequality. I really need to kind of separate this information. So yeah, I don't have a good motivation for you other than I've done it different ways and realized that this was probably a better way to go. So check this out. I'm going to rewrite this whole expectation as the square root of this entire expectation squared. Right, that's certainly equal to the line above. And you might recall the Cauchy-Schwarz inequality. I'm a little short on time, so I usually at this point would kind of recap that for you, but I'm not going to recap it. So go back and check it out. I'm going to write CS for Cauchy-Schwarz, and this is less than or equal to the thing inside is less than or equal to the expected value of this thing squared times the expected value of this thing squared by Cauchy-Schwarz. I'm assuming things are scalar here, so this is just an absolute value. If that quantity is going to be squared, I don't even need it. I'm going to rewrite this line as epsilon plus the square root of the expected value of theta n hat minus theta naught squared times, now this one I'm going to rewrite. This is an indicator and it takes the value 0 and 1. And when you square it, that's still the value 0 and 1. So the indicator squared is 1 whenever the original indicator was 1. And same thing for 0. So I can just drop that squared just because it is 0 or 1. And when you square 0 or 1, you still get 0 or 1 right back. Okay, this first thing here is the mean squared error for theta n hat. And you know I'm going to use that bound, that C, on the next line. But first, let's look at this expectation. I can't remember if I'm pretty sure, but I can maybe confusing you with my other class, whether we've done the expected value of an indicator. It always ends up being the probability of the thing being indicated. A quick aside with something simpler looking, the expected value of the indicator that says that x is greater than or equal to 3, even if x is continuous, the indicator is not continuous. It's a discrete random variable taking on the value 0 or 1. So it's 0 times the probability this indicator is 0 plus 1 times the probability that this indicator is 1. And so the 0 term goes away, and we just get the probability that this indicator, sorry if I did this before, is 1. But that indicator is 1 if and only if the event being indicated happens. So this is the same as the probability that that event happens. So here's what I was saying. The expected value of an indicator is always equal to the probability of the thing being indicated. Always. And I'm going to use that. I'm going to go back up to where we were and use that right now. This whole thing is less than or equal to the expected value of epsilon plus the square root of c. So I'm breaking this up and using the fact that the MSE was less than or equal to c. And then the other part is the square root of the probability of the absolute value of theta n hat minus theta naught being greater than epsilon by what we just discussed. Okay, what are we trying to show? We are trying to show that the MLE is asymptotically unbiased. If I have convergence in probability, which to have that, I'm going to need a condition. We know that a sufficient condition for convergence in probability is that the variance of a certain log of PDF is finite. So under the regularity conditions for convergence and probability, with the additional regularity condition that we're going to assume this variance is bounded, with those two conditions, then we have convergence and probability of our MLE to the true thing. So the probability that this distance is greater than epsilon is going to 0. So this goes to 0 as n goes to infinity if the variance of the log of f of x1 and theta is finite. Because that was our previous condition in our list of things that we needed to get convergence in probability. Then theta n hat converges in probability to theta naught. And that probability is going to 0. Now let me pull it all together. The limit as n goes to infinity of the absolute value of the expected value of the MLE minus theta naught is less than or equal to the limit of this thing. And this is a nice bounded constant, and that part's going to 0, so we get less than or equal to epsilon in the limit. To finish this off, since epsilon greater than 0 is arbitrary, or was arbitrary, we just chose any one of them, then we can get this as small as we want, which means that this limit is going to 0. Why is that? Because if you think the limit is going to 0.000000010090006, choose your epsilon smaller. You can't get a limit here that's guaranteed to be above 0. It must go to 0. So this implies that the limit as n goes to infinity of the expected value of the MLE is equal to the true parameter that generated the data. And that's what we wanted to show. So two regularity conditions used there. One we got from our previous property, and another we introduced as we went along, and that was the fact that the variance of the MLE needed to be bounded. Because what good would it be for the variance to go to 0 if this is blowing up? We wouldn't be able to get this nice clean result at the end. Okay, we have two more things to prove, but it's getting a little, I don't know, I love today, but maybe it's getting a little intense and I want more of a balance. I never want a balance between theory and application. And this is still going to look theoretical, but let's do another MLE example. And I want to do one that maybe looks a little trickier. I got not this particular problem, but I was motivated by a problem I saw on a qualifying exam for statistics PhD students. And that doesn't mean it's hard. It just means it's different, which is that going to make you freeze or realize that you know how to do this? So uh, here is a break from what we're doing and an MLE example that's kind of fun. Suppose we have a random sample x1 through xn from the exponential distribution with rate lambda. I'm gonna let little c be a known constant. This has nothing to do with that c from the previous proof. And let's assume that it's greater than 0. I'm going to define a new list of random variables y1 through yn as, so the ith one is going to be 1 if the ith x is greater than c, and yi is going to be 0 if the ith x is less than or equal to c. Suppose we only get to observe not the x's, but the y's. Observe y1, y2 out through yn. We do not get to observe the x's. Let's find the maximum likelihood estimator for the underlying parameter, the lambda, the rate parameter for the exponential distribution, but we don't get to see those random variables. This looks different. We haven't seen, this might look very strange to you, but it's not hard. Just keep breathing and work your way through it. We only get to see the y's. So our maximum likelihood estimation needs to be working with that as your data. So your likelihood is a function of the unknown parameter, and the data is always hidden in there. So let's write down a likelihood here using the y's. Note that y1, y2 out through yn are IID, right? If the x's are independent, then each of the y's is independent because each y is defined in terms of xi and not the other x's, and they're also identically distributed, but they are zeros and ones. The y's actually have a Bernoulli distribution with some parameter p that we're going to figure out right now. P is supposed to be the probability that any one of these is equal to 1. But any one of the y's is equal to 1 if the corresponding x is greater than c. For the exponential distribution, I assume you know this probability already. I'm just going to write it real quick though. The integral from c to infinity of lambda e to the minus lambda x dx. This is going to turn out to be e to the minus lambda c. So that is in here. This is how the y's are related to the lambdas. And we get to observe the y's, so that's what we're going to use as our data to estimate lambda. I think that we should just go for an MLE for the Bernoulli distribution. And then from that, how do we get lambda out of P? So if you look at this relationship, you can solve for lambda. This implies that lambda is the negative of 1 over C times the log of P. So my lambda is a function of P. I'm going to call it tau of P. I define tau of P to be this negative 1 over C log of P. So step 1 is going to be to find the maximum likelihood estimator for P, and I'm going to call it P hat. You could put the subscript N if you want, but I'm not doing any convergence here, so I don't need to see that N. And then by step 2, we want to use the invariance property of MLEs. And we'll get the MLE for lambda. So every hat in this problem is an MLE. I'm not writing like sub MLE because we're not comparing with different kinds of estimators like method of moments or guesses. So just to be clear, every hat in this example is an MLE. This lambda was equal to tau of P. So I want the MLE for this, but the invariance property says that if we're working with MLEs, we can just find the MLE for P and plug it into tau. This is tau of P. So we'll find the MLE for P and then plug it in and we'll be done. I don't know if we did the Bernoulli. We might have. I'm going to be kind of quick on this because I don't think you need practice on this. But what is the MLE for P? I've got Y1 through YN, IID, Bernoulli with parameter P. So the PDF for one of these is P to the Y, 1 minus P to the 1 minus Y. And then an indicator that says we take on one of two values in this discrete set for Y. And P, the parameter space, is 0 to 1. The joint PDF is going to be, because they're IID, we'll get that from the product of these. So we'll get P to the sum as I goes from 1 to N of the YI. And then 1 minus P to the N minus the sum as I goes from 1 to N of the YI. Get this out of here. We'll also get a product of indicators, but if you recall from our MLE computations, if there's no parameter in the indicator, we could just sort of ignore it. It's going to go away. And if there was a parameter, we sort of keep that information on the side. So technically, this is a multiplicative constant for the PDF when you think of it as a function of P, but I'm not even doing that. I'm just saying, just ignore it, except if it contains information about P, then ignore it for the moment. So a likelihood is P to the sum of the yi's, 1 minus P, N minus the sum of the yi's. The log likelihood is the sum of the yi's log of P plus N minus the sum of the yi's log. I'm pretty sure we did this. I'm going to take the derivative with respect to P of the log likelihood. I get the sum of the yi's over P. That comes from the derivative of the log of P being 1 over P. And the derivative of the log of 1 minus P is the derivative of the inside, which is negative 1 over 1 minus P. So we end up with a negative N minus the sum of the y's over 1 minus P. And we want to set that equal to 0. Now you solve for P any way you want. I usually multiply both sides by the common denominator, and then I get some cancellation. So on the left side, I've got the sum of the y's times 1 minus P minus N minus the sum of the y's times P. And on the right side, we still have 0. Yeah, so if you run things through, you're going to get a lot of cancellation. You're going to be left with the sum of the y's minus NP equals 0. And if you solve for P, and then ultimately make everything capital, put a hat on it. The MLE for P is the sum as I goes from 1 to n, capital Y sub I over n. In other words, it is the average of those y's, the average of the observed zeros and ones. So to finish this off, B, maximum likelihood estimator for lambda is lambda hat, which is tau of P hat. So lambda was equal to a particular function of P, which was negative 1 over C times the log of P, by the invariance property of MLEs. This is tau of the MLE plugged into that function. This is negative 1 over C times the log of that P hat. And to be a little more specific, this is negative 1 over C times the log of Y bar. That is the MLE. It wasn't hard, but it was different. And I could see that you might or might not, but sort of glitch at the beginning of seeing this problem. What do I do? First, you realize that you don't observe the x's, so you can't make a likelihood based off of those. Instead, make a likelihood off of your observed y's and get the MLE for that Bernoulli parameter and then translate it back to the MLE for the original lambda, which is what we did, which was totally cool. So I know we need to verify conditions, but this MLE existed. You should check the second derivative to make sure we didn't minimize anything, and is unique. I only found one critical value when taking the derivative. And there's a lot of conditions to check, our regularity conditions, but it will hold here that this MLE converges in probability to the true lambda. We do get consistency, and we do get asymptotic unbiasedness. Now, if you don't buy that, because I haven't verified those regularity conditions, then you could actually show both of these from scratch. We've done both of these types of problems before. You know how to find the expected value of this. You would have to find the expected value of this. And I'm not saying it would be pretty, but you could verify this and this from scratch if you don't want to take those results from the properties of MLEs because you're worried about the regularity conditions holding. In this class, I'm not going to try to trick you. So I don't know what to say. If on homework or an exam, you are asked to show that this is a consistent estimator of lambda, you should ask me even during an exam, can I just use the fact that MLEs are consistent? And I'll probably say yes. Can you show it from scratch? Of course you can. But I'm out of time. So next time, we're going to prove properties 4 and 5. And then we're moving on towards the UMVU, the uniformly minimum variance unbiased estimator, the greatest estimator in all the land. No one can do any better. We're not going to hit it next time or the lecture after that. We've got to build up quite a bit of machinery that we can use for other things as well, so it won't be such a long buildup for just one result. Next time on mathematical statistics.